Hello everyone and welcome back to Lee's R&D session number 2. So in this video, Lee, you're going to begin talking about height maps and why we are switching over to those, correct?
Right. In the last video, we were talking a little bit about how we were going to get away from purely pseudo-random number generated type terrain into something that's going to be derived from height maps. And that's pretty much where we wrapped that one up to start this video.
Yeah, I kind of had to cut you short because, I didn't want things to get carried away and you start talking too much about what was in this video. So now that we're here, why are we moving away from the way we're doing it now and over into height maps?
All right. Well, there's several advantages that we're going to get by using height maps, particularly speed, that we wouldn't have if we were doing a procedural method. If you've ever messed with any type of random noise or any type of random number generator, whether it's a pseudo random or a true random number generator, which is really hard to do in code, but it usually gives you a really even disbursement of numbers, but it just doesn't look like terrain.
Mm-hmm.
So it doesn't have enough uniformity across it to simulate terrain. So what you can do is do some sort of noise, whether it be a fractal noise, a Perlin noise, simplex noise, or one of the many other noise algorithms that are out there, or combinations of them. Those can get you closer to a real looking terrain. If you combine that with something like a Voronoi graph or cell chart, then you can get things like mountain peaks and valleys and rivers, and you get even closer to a real looking terrain. And then on top of that, if you start simulating things like hydraulic erosion or thermal erosion, we get even closer. But as you probably are picking up, I'm saying we start off with something unrealistic, and then we do a little bit more, and some more, and then some more. And as we keep doing more and more and more to this to get closer and closer to real looking results, all of these things have to be calculated. These are number crunching procedures. And the more things that we have to do, the longer it's going to take us to generate this terrain. This terrain we want to be dynamically generated on the fly. We want to be able to set our player loose anywhere inside of our world and then have the client build the mesh in real time. If the client software has to go through and calculate this mass amount of data to build each terrain patch, we're going to very quickly bottleneck the system to the point where it's doing nothing but generating terrain.
Mm-hmm.
Now, if we were building something like Vue or L3DT or some other type of program that's whole purpose was to build these beautiful landscapes at which we could then texture render out for a still or render them out in frames for an animation, it'd be great. But this is supposed to be a real-time game, not so great.
Right.
So what we're going to do is we're going to, well, I guess we could call it cheating. It's just a different way of looking at it. Instead of random using a pseudo random generator and all this procedures, what we're going to do is we're going to take a couple of textures. Those textures are going to be predefined and saved out by an artist or a programmer or yourself or whoever wants to build these height maps, and we're going to put them in a system that we can use those to build massive landscapes very, very quickly just by sampling different points in the height map at different scales and different amount of weights and blending them with the other samples. And I'm going to get into exactly what we're going to do here shortly. But while sampling a multiple random points, it's not going to work because we're still going to get back to the point that it's going to be jumbled and it's not going to be coherent. It won't look right. But what we want to be able to do is sample in such a way that we can give an artist the ability that says, I want an ocean here. I need a continent here. I'd like to have a mountain range here, and maybe some lowlands here, maybe some plains over there, and give them this macro level ability to design the world without having to worry about, well, there needs to be a bunch of hills here and they've got to be exactly this high, or there should be a peak or two out here and they need to be this high. What we want to do is give that artist that macro level control without them having to worry about every little minor detail of the world. Let the system procedurally generate that information, and then another artist or the same artist can come back and fine tune that with the trained sculpting tools that we'll be looking at in a future set of videos.
Okay. So you want to
So,
jump over to Photoshop real quick and talk about the textures right now? Just show
sure.
them to them?
Yep, I'll
Yeah,
give
it
it a
looks
shot.
like I might have
Actually,
to.
you might have to swap over for me.
There we go.
Hey, that kind of looks familiar.
Maybe.
Well, I needed something to use as an example, so we had some sort of landmass that, wasn't the entire size of the world, but a little bit more manageable. But I definitely wanted something that had some sort of definition, maybe some islands, some coastline, some lower areas, some higher areas, and some even more
Let me give you a
altitude
pointer. There we go.
up, and even some more altitude. So
And
I
with
figured
that,
this
and,
little
and with
land
that, real
mess.
quick, let me go ahead
Yeah.
and throw this in. So for those out there that have never worked with height maps before, so as you're just kind of mousing around saying and higher and lower and oceans, go ahead and describe how the colors between black and white drive altitude.
Okay. Well, in a height map, most height maps, it depends on the system. They vary a little bit here and there. But in the system that we're going to be using, we're defining black as the lowest possible altitude that anything in the terrain can be. In this case, here would be all black based off this height map, would be the bottom of the ocean with a value of zero point 0.5 or 127, depending on if we're looking at a bite or a float, would be halfway between the bottom and the top, would be sea level, where 1 or 255, again, depending on what system you're using, would be the highest possible altitude in that height map.
Okay.
And everything in between is going to define the altitude of that point in space.
Okay.
Now, what our system's going to do is we're going to have a field that's going to hold a max altitude. That's essentially going to define the highest altitude that anything in our world could possibly ever be. And when we get into the equations, I'm going to do some math magic that will take that number, divide it by half, and then the lowest elevation below sea level will be half of our max altitude.
Okay. And why are
So
you doing that?
just because in a game it kind of is cool to have mountains that look really, really high, and for the most part, you're never ever going to be able to get up there. But in the ocean, if we want to have the ability to swim underwater, we don't want to have the Marianas Trench at the bottom. We like to have it not quite so cavernous.
Hmm.
So by cutting the altitude in half, we kind of smooth out those really, really deep spots and give us a little bit more rounded bottom to our oceans.
Okay.
It just seems to look very well when you render it out.
So then right now with this, if we were to come over here and start zooming in,
Hmm.
and then we get into areas like this where we've got black, so we know that's going to be our lowest point. And now, starting right in this area here, this is no longer black, but it's still very dark. So is this area right here going to actually give us beaches?
Well, it won't give us beaches per se, mostly because we're going to have to edit this image because the levels of this image aren't going to correspond very well with what we're going to be bringing in.
Hmm.
Mostly, there's too much differentiation between black and white. So this image goes all the way from black. So if we were to take it as is, our ocean, all that black area would be a flat bottom.
Right.
And then the white spots would be the highest altitude, which would look like a whole bunch of peaks about the size of Mount Everest. And last time I checked, there are nothing approaching Mount Everest in the UK. So what we're going to do is we're going to do some color correction to this to flatten out and even out the tones.
Okay.
And we're also going to bring it up so the bottom of the ocean isn't quite so deep. We're going to allow the second part of our calculations add noise, which is going to give us a contoured seafloor without having to worry about adjusting this image so that we had information for below sea level.
Okay, well, let me ask you this. Now, that's not this, whoops, that's not this other map you're talking about, is it?
Yes,
Okay,
that
all
is.
right, I thought so. But this isn't just the seafloor, is it?
No, this is a noise map.
Okay, so
The,
go ahead and
the,
talk about this because this is pretty
right,
important.
right. Where the first map is a base map that says, okay, this is where oceans are, this is where land is, this is where mountains are. This is a map that is tileable in both directions and is used in many passes. In our case, it's going to be used in 4 different passes at different scales. And we're going to sample that information and we're going to weight those samples and blend them in with the other samples to add differentiation in our terrain. So, with our world being so large, in our case, the test world that we've been playing with is about 73,728 meters across.
Mm-hmm.
But that map of the UK that I have is only 2,048 pixels by 2,048 pixels.
Mm-hmm.
So the numbers don't work out where I can have 1 pixel per vertex in our world. So what we get is a very stair-stepped look to our world. And when we start coding it, I'll show it to you so you can see what happens. But what we need to do is mix it up so those vertices get displaced some so it looks like a real landscape. That's the purpose of this map. So what we do is I've taken L3DT, used it to generate a different map, and set it up so it would be tileable. And then I adjusted its colors because I don't want anything to be completely black. And I don't want anything completely white. I just want a nice little variation to the height around the middle. So some things go down lower, some things get picked up. So I've compressed the color schemes right around middling gray.
Okay.
And like I said, we'll sample that multiple times and it gives us a cool little effect that we'll get to. Now, the nice thing about this technique, as opposed to doing it purely procedural and using noise to generate and drive most of our terrain, is the fact that it's very fast to go, I need the point of this texture at this X and Y location, return that information, and add it to another number.
Mm-hmm.
And so we can do these lookups, and you figure most or all of our terrain does one base lookup, 4 noise lookups. So that's 5 lookups total. That makes up a height sample. Now from there, I need to average the vertices to smooth out any little noise irregularities. This is to prevent any one of the vertices from looking like little spikes in our terrain. So I do 7 of those samples. So I sample the 6 surrounding vertices and I average that with the vertex in the middle to smooth it out. So now you're talking about 5 different samples times 7. So I'm doing basically 35 lookups and sets of calculations to get that information. Now, if you were to look at something like the old terrain generator that I had, where I had multiple iterations, to do the same equivalent lookup for all 7 of those points, average them together, would have been several hundred operations as opposed to 35.
Gotcha.
So we get a very big performance. The other really deciding factor of going this way is that each of these height maps are fairly small. I believe the height map, the noise height map, is about 532 kilobytes in size.
Mm-hmm.
And I believe the UK original PNG is even smaller than that, but I can't see it from here.
Okay. Um, Let me see. What is the size of that? It is actually it's just under a meg.
Oh, is it? Okay, so in other words, it's using all four channels. So in a final image, I would probably strip out all the other channels and just use a single channel, which would then cut it down.
Hmm.
Hence, what happens when you pull an image off the internet.
Yeah.
So,
All right.
but but in total, this gives us the ability to give us a world that's, in this case, about 2,100 square miles in size, non-repeating. And even with the unoptimized height maps, we're still only at about a meg and a half worth of data. If we're to actually or build out that information in real time and save it, it would take several hundred gigs to save that same type of information.
Gotcha.
So, but let's see. I'm trying to think where else that you need to know. There are some things that we're going to have to do with sampling, but I'm going to cover those more when we get to this section. What I mean by that is, if you look at our maps are 2048 by 2048 pixels across. Now, our system is not always going to take an X and Z location in the world and be able to exactly map that to a pixel location. Those numbers will occasionally fall in between two pixels.
Now
And technically,
this is because of the scaling.
uh, well, because of the scaling and just the fact that if I were to look at a pixel, if you could zoom in to about the pixel level on this image.
Mm-hmm. Woo.
Oh,
Hang on.
no.
No, I'm backing us back away. I want to go up here, over here. Thank you.
And unfortunately, I see a giant sheet of gray. But can you demonstrate two different pixels side by side
Well,
at the
yeah,
resolution, or is there not?
I'm trying to hunt for one. Um, I mean, we're zoomed all the way in, but the coloring is.
Oh, use the UK map one. That one's got more differential because the noise map is blended together.
Yeah, here we go.
Yeah. All right.
Nice.
So what we end up with is in between two different pixels. Let's see, say this pixel and the pixel right next to it
Wait, go ahead and move your mouse again.
here,
Uh-huh.
and then this pixel right
Uh-huh.
here. To me, one looks like a light gray, one looks like black, but
Yeah,
I don't
pretty
know what you're
much.
seeing. All right. So let's say for some reason we've got a vertex that maps out numerically. Let's say this pixel right here is at 100 and this one is 111
Mm-hmm.
on the X. And our vertex works out to be 100.5
Mm-hmm.
mathematically. Well, then you're sitting there, it's like, oh, well, do I use the color for this pixel or do I use the color for that pixel? Either one would be incorrect. So what our system's going to do is go, oh, okay, well, I'm halfway in between this pixel and this pixel. So it's going to take the average of these two pixels because it's halfway and go, okay, the color for that point or the height for that point is going to be halfway between this height and the height next to it. If it was a quarter of the way, closer to 110. So let's say our value, or sorry, 100. Let's say our value was 100.25. It would take the value that was 25% of the way between the two, biased towards the pixel on the left. So it would be a lighter gray. It would be darker than the pixel on the left, but lighter gray than it would be if it was halfway.
Right.
This is called linear interpolation between the 2 points. We're going to do that not only for the x-axis, but the z-axis. So if we've got points that fall in between any one of 4 pixels, it's going to calculate what the interpolation of that height would be in the center of those 4 pixels.
Okay.
and it will return that information. It'll give us a more accurate representation of what's going on in the height map, which comes in handy when we start scaling out these numbers, because some of the numbers that we're going to be using for scaling are going to be quite large. I think, can you bring up the calculator?
I
I'm going to move my mouse over here.
think that we had it. Hang on, there it is.
Right, and I need to find here. All right. Okay, let's see if I can type. There we go. All right, so our map is 2048 pixels across. The base map, the map of the UK that we've got, we're going to scale that 73. Basically, we're going to take it all the way up to 73,728 roughly. So you're talking about taking 73,728 divided by 2048. We're going to scale up our texture 36 times to make our texture of the UK fit our R&D world.
But
So
that's what I was trying to reference a second ago when I was talking about this major need for sampling, is because we're scaling this thing up so large
right,
that
which
obviously
is
between just 2 points, we're going to have a lot of vertices that are going to fall.
right. Because what would happen is at this point that means that every at the equation at the base map, every point on our map is the equivalent of 36 meters. And at the density that we're working with, we're using a spacing of 3. So basically, every pixel of our height map is the equivalent of 12 meters across. So we're not going to have enough resolution, which is why we're going to do multiple samples with a noise height map. Because if you were to look at it, every vertice would be, or each pixel would be 12 across, which means that for every pixel, we're going to have a plateau of altitude that's
Right.
12 meters across. It
That.
looks very stair-stepped.
Yep.
It looks like the race paddies that you see, or pictures of race paddies you see, where they're all plateaued and flat and go across and raise up.
Hmm.
You've probably seen those. But that's what the world's going to look like when we scale this up before we throw any of the noise sampling in. And then what I'm going to do is we're going to go through, we're going to set up the initial methods in the next video to start building this system up. And we're going to sample just the base map so we can look at that. And then we're going to add to it the ability to add in the noise maps layer by layer.
Okay.
And we'll see how that gives us a nice looking terrain. And the nice thing with using the original base map as well as a height map that isn't just a random noise that we pull out of, say, Photoshop. If we use something like L3DT or any of the other terrain generators out there, is we get the effects of erosion for free.
Right.
So all that is essentially pre-calculated. We're just sampling it at different resolutions and blending it together.
Hmm.
So
Okay. Does that pretty much cover everything that you wanted to talk about here?
I think so. It's like when I
Okay.
think it'll work. It's kind of hard to visually grasp it with just talking about it. So we probably should throw some code together so we can see some pictures.
All right. Awesome. Well, with that, that is going to wrap up this video. Thanks a lot.